Hi, hello everyone. Welcome to this workshop. Can everyone hear me? Maybe you can type on the chat on the right yeah, perfect. Okay, so welcome everyone. Audio is good, great, loud and clear, perfect. Everything's okay. Someone said choppy audio. I hope everyone else seems to say it's okay. Cool. Sounds good. Okay, then we will go ahead and get started. There are two members on the chat / on the Q&A. There's going to be Valentine and Mary McGarth here. They might help out with the fielding of questions later on. Alan Edelman is here. Hi, Alan. Hi. Okay, so we will go ahead and get started. I'll share my screen first and just give you an idea of what's going to happen in the next 3.5 hours. So the pipeline or how things will go in this workshop are basically we're going to divide it into two chunks. The first chunk is just introducing basic things on how to run a profiler in Julia and how you would normally benchmark your work in Julia if you have some code that you want to understand how it's running in terms of time or memory consumption. We're going to use benchmarking tools. And then we're going to go over nugget examples. This workshop is going to be highly led by examples and not by theory or building up on like one item over the next item. It's just going to be standalone independent items, each example alone. And we'll see how many we'll get through. There's about 20 examples here. So hopefully we'll finish all of those in 2.5 hours. And then we'll take a small, we'll just recap the pipeline of making your code, use the best, like the most optimal things in Julia. And then we'll take a break and then come back to demo how to call Python code from Julia and how to call C code from Julia. Just to take a step back and recap of what's the goal of this workshop to start with. The goal is a lot of times people move to Julia and there's a burden to overcome when you first move because supposedly you've probably had a lot of code in another language. And there's also the burden of making sure that you're actually using the most optimal or the best tools that Julia offers to you. So the goal is to highlight those tools and basically give you the basis that you will need to transition into Julia. So it's somewhat beginner level, but also we're not going to be covering syntax and stuff like that, but hopefully throughout the workshop, you will pick up on the syntax if you haven't seen it before. Okay, so for now, we'll just jump into the demo. So if you can locate this file or this GitHub repo here, the handle should be easy. My handle nassar.huga, and then JuliaCon 2020 files. I'll keep the screen up for just a couple seconds, and then we'll go to GitHub and just check out the demo. Perfect. Someone may already sent the link. As you're locating this GitHub repo, I'll introduce myself. I haven't introduced myself yet. My name is Huda. My background is I'm currently a postdoc at Stanford University, and I work on my current work is more focused on data science-y kind of methods on biological data sets. My actual focus is on data science in graph analysis. So whenever the data is of type graph, that's mostly the things that I focus on. And I started using Julia, I think my first year of my PhD about 5 years ago. I've been using Julia for all of my research code and all of my work ever since then. So I'm a big fan of Julia. Okay, so I will leave the screen now. And go here. Okay. Was everyone able to locate, or can people still see my screen, by the way?
Yep, I see the locate the GitHub repo slide.
Sorry?
I see the locate the GitHub repo slide. Is that what
so
I
you
should
don't?
be?
No, okay, let me. Okay, I guess now I'm just sharing all of my screen. So. Okay, perfect. People seem to have found the link. Again, it's over here. And I think this is a good time to just go ahead and get started. So for the first thing, what the first file to start with is going to be performance case studies, IPython notebook over here. If anyone's having trouble with getting the notebooks, maybe you can chat on the chat box and ask questions, but hopefully everyone is able to get them. Okay, so we will start with the first GitHub link here. I will actually go to my local version of it. And we will, let me make sure to restart. Okay, good. Okay, so throughout this notebook, we're going to, again, have about 20 examples. And one thing to know is everything's going to be labeled or tagged kind of using GitHub type mentality. So we're going to have tools, types, and memory. So everything we're going to cover, it's either going to be a tool to know how to benchmark and, or for instance, like understand your code better. Or it's going to be a memory issue. So we're going to understand how memory is structured in Julia, or it's going to be a types issue. Okay. So we will start with the first item here, and the first item is benchmarking. So if you want to benchmark your code in Julia, one thing you could do is use this benchmarking package, BenchmarkTools.jl. There's a link to it here. And there are two key things you might end up using a lot in benchmark tools, which are these two macros, @btime and @benchmark. And we'll see what each of these items look. And then we'll cover two main parameters of the package just a second later. So these are the four main things we'll cover for now. Okay, so the first thing is we're going to import the package using benchmark tools. And the way we will do it is to benchmark just like finding the norm of a matrix, so norm of A. So we're using the linear algebra package here too. Now, if you've used this package before, let's see. Okay. If you've used this package before, you might be thinking, maybe I did something wrong here, which is I didn't interpolate the matrix A. And there's a reason I didn't do that. I just wanted to show you something. So let's go actually. So here's what I did here. I just created a matrix A, which is a random matrix of size 1000 by 1000. And then I just timed how long it's going to take to find the norm of A. Now, as we can see, we're going to get a few things over here. The first thing is the time it took. And the second thing is how many allocations and the number of bytes that were used or created to create the norm. So great, that looks fine. One thing you will need to know when you're timing anything inside a function, though, or inside a different scope is, for instance, here, we're going to do the same exact thing, except that we're going to do it in a function. So here we're creating a matrix B, and then we're B timing it. So like literally the same exact thing It can be even more exact if I add the zeros, but that's not the point. So I'll just skip it for now. And then the next thing I will do is call the function. So I created the function and then called the function. And now this is going to generate an error. And the reason it generated an error is essentially norm of B here, it's actually looking for something in the global scope. So actually, if I add A here, it's actually going to work because it is looking in the global scope and the global scope had an A in it. So that is interestingly going to work fine, but that's not what we want. So what we want is to find the timing of B. So what you should do when you're timing things in local scope or in general, actually, is to interpolate these variables. So instead of just passing B, you want to send the $sign B. So this is how you're going to run it here. And now it's going to work fine. Great. OK, so the next thing we will do here is, again, we're going to run just have a bigger matrix A, and again, run at benchmark. We can do either of these syntaxes. Syntax is fine. So B is going to be, we're going to use the benchmark macro here. OK, so a few things will happen here. As I'm running the benchmark macro, it's actually going to run multiple times, and the multiple times will this time be recorded. I'm not going to get just one number. I'm going to get multiple numbers. So as you can see, B is now a data structure where if I type B dot and hit the tab button, I will see multiple things. I'll see times, allocations, and memory, for instance. What I'm interested in here is the times macro, the times value. I think I have to do, let me remember, I think it's 10 to the minus 9 to get the values in seconds. OK, great. So yeah, these are in seconds. We can get them in milliseconds with 10 to the minus 6. But anyway, the point here is we get a vector instead of actually getting a number. And now what is this vector? Why do we have 56 numbers and not more numbers, for instance? Can I increase the font size? Yes.
Zoom in a tiny bit so the font's a little bit bigger.
Yes.
Thank you.
OK, is this better?
Yep.
OK, great. All right, perfect. So yeah, B dot times, we got 56 numbers. Why do we get 56 and not a different number? What you will notice here is, for instance, one thing you could determine, we'll see why we got 56 in just a second, but before we get to that, let's see if we wanted to change the number of sample runs we want to run. You could change this value, samples is equal to 10 here, for instance. So like if I run this again, we're going to get 10 numbers instead of whatever we got earlier. Now, this is the two other things that I wanted to cover aside from at benchmark and at btime, which are the variables that, or the parameters that determine how this package is going to run. So here, for instance, I got btime and it was 10 times. One thing you can see here is, for instance, if I actually type benchmark.samples, the default here is 10,000. So if I actually run at btime of, honestly, I'm just going to do something really silly, but you will see that we will get okay, let me just. Oh, that's why I'm not choosing benchmark. Okay, so you'll see that we got actually 10,000 samples. So the default is 10,000 samples. But this time here, we didn't actually get the default 10,000 samples. The reason it wasn't 10,000 samples is because of this other parameter, which is BenchmarkTools.default seconds. So what this will do is, hypothetically, it's going to run 10,000 times if the 10,000 times are going to fit in under 5 seconds in this case. But if I reached 5 seconds and I couldn't run 10,000 times, I'm just going to return what the number of times I was able to run, under the condition that I will return at least one instance in benchmarking. You can also change these numbers. So like if you actually want to increase that threshold to 100, you can decide to run it to 100. I'm actually not going to change that here because I do want to keep it 5 seconds for the rest of the notebook. But you can play with this number. You can change it if you want to make sure you can run up to 100 seconds. Just keep in mind that you will always, whenever you hit that number, the default number you set here, this is when you will stop running, whether you have 10,000 samples or 10 samples. If you finished your samples, great. If you didn't, it's going to stop. Okay, I think that's enough for now. This is basically the main components you might want to know about benchmarking. Let's look at the chat really quick. Okay, great. Okay, thanks, Valentin. You said it was benchmark. Okay, great. So that's just a recap. These are benchmark tools are a great tool for benchmarking. Don't forget to interpolate especially when you're working with local scope, and you can control a bunch of parameters. There's more in the benchmark and this link over here that I have. But also, I think the two main things that I often use is the number of seconds and so the time and the number of samples to run. Okay, moving on to the next important thing to do while you are working with code, which is profiling your code. So here, what I will demo is profiling some random file I found on the internet. So actually, I don't know if you know this resource, I think it's called Rosetta Code. If you go here, it's basically just like you can go and like find a lot of tasks, and for each task, or actually let's do things by languages, and then for each language, whether each language or each task, you will go to, for instance, Julia, and then you will find a lot of like popular computer science-y problems that you often see in undergrad, or just common problems written here. I honestly just randomly picked, I think one of the top ones, I think I picked this 15 puzzle game. I just went there and I took the code and just copied and pasted it. There was one issue with the code which I had to fix, but the file you have over here should be the fixed version. So if we go to this over here, yeah, exactly. So this is where it was obtained from. I did change two things from the original file. Size was renamed. That is not, we shouldn't be naming variables as size. And instead of exiting if the player stops wanting to play, it's just going to return. So I just changed a couple things. I don't take responsibility of this code. I don't know how good it is or bad. I didn't look too hard. So I just picked it from the internet so we can play around with it. Great. Okay, so now that we have the file that we wanted to profile, this is how things are going to go. So I'm just going to include the file here to show you what the file looks like. And I'm actually going to hit 0 to not play the game. I am really interested in profiling. So have a working solution. I do have a working solution. I just tested it. That's fine. Well, I didn't really test it, just check that it's working. I assume it's working. You can trust me, it's working. And then the next thing I will do is go to the terminal and do this from the terminal, actually. So I'll start Julia with this key over here. So let's go to the terminal And let's do Julia. Let's copy this. And then here you can decide on one of three things. Usually it's either user or all or none. Oh, I need to increase probably my font here too. Okay. All right, so none is actually the default. It's not tracking anything. So we'll go ahead and do user. If you do all, it's just like all would work here actually as well. But for all, it's just gonna track all the other Julia. Like it doesn't necessarily need to be your own file. So user would just do here. So do this. So now we're doing track allocations. Let's just follow what we have here in terms of steps to show you that like if you follow these steps, everything's going to work fine. The next thing is we will type using profile. And then the third thing, again, I'm just going to actually run the file once. And I will not play the game. And run the code, that's fine. And then the next thing I will do is actually to clear any data. The reason we might, or you might want to sometimes do this is sometimes like if you're running multiple things over time, everything in memory is actually being allocated on a buffer, or like the buffer is accumulating all this data that you're using. So it's good to just like have a fresh start before you clear everything before you run the profiler. Okay. And then the last thing I will do is I will add profile what I actually want to profile. I'm going to profile this. Okay, great. So this should have been profiled at this point. And if I hit exit here, I will leave the Carry on Julia session. But what will happen is if you go to your Finder, you will find out that, let's see, yeah. You will find out that you actually have this file here. It's the same exact file starting name, but it has the .mem at the end. So what this is really just for every line on the left-hand side, there's the number of bytes that were used for that line. So if you, yeah, this is, yeah, for each line, there's the left-hand side is the memory or the number of bytes used. Great. Okay, so going back to the notebook here. Yeah, this is really all you need to know about profiling, or I mean, not all you need to know about profiling. There's always more things to learn. But in general, if you are interested in profiling your code, this is a standard way to do it. Just follow this pipeline. Okay. Moving on. The next thing is, okay, so far we've covered two items, which are the benchmarking and profiling. And these might come up later in the notebook. So just bear in mind that these are probably the only two examples where we might go back to them. But the rest of the notebook, every example is independent. Okay, so let's just talk about types. So in Julia, you might know already things have types. So if you type a matrix A, the matrix A is actually has, say, like if the element type in the matrix is a float, then it's an array of size 2 and the element type is float. So there's two distinctions between in terms of types. There's something called an abstract type. An abstract type is something like real, and a concrete type is something like N64. So what does that actually mean, or how does that translate in practice? Okay. So, okay, so here what I have is a function that will just plot or draw what the subtree types of each type I'm gonna type will be. So one quick thing, usually, so the biggest, or if you want to think of the types and Julia as a tree, and you can think of it as a tree, the kind of the root node is of type any. So anything under any is just going to be like under the tree. One of the items, one of these things is actually number, and this is one interesting thing that we will look at. One thing, like if you actually type this, if you define this function and type it with type any, you're going to get a really, it's going to print for a really long time. So probably don't do it, or do it and know that it's going to print for a long time. So I'm just going to do it with number here to show you how things are. So for instance, I mentioned real is, for example, an abstract type. For instance, like float 64s are concrete types, and anything here is really a concrete type, like int64. Any of these items are concrete types. Bool is a concrete type. So this is really a good distinction to realize in while you're typing your code. One other thing you can always, if you're wondering if something is a concrete type or abstract type, is you can actually call the isConcreteType function, or isAbstractType function actually also exists. So you can do here is abstract type real. Okay, great. So yeah, real is of abstract type. Okay, so now that we've introduced what a concrete type is and what an abstract type is, let's take a look at one quick example here. So we're gonna write a function to play this game. The game is basically, we're gonna toss a coin, and if the coin is above half, the game is won, and if the game is not above half or below half, the game is not won. But the key thing is we want to record the number of or the actual indices of the games won. So I don't want to just know how many games we won. I want to know what are the games we were winning. So this is one way to do it. This is probably a really bad way to do it, but this is one way to do it. So the way I'm doing it here, I'm just deciding how many games we want to play, and then we're declaring this vector that is empty here. From 1 till the number of games, we're going to toss a coin. And if the coin is above or equal to 0.5, we are going to push into the games won, which is the vector that we're interested in saving all the games won in. And then eventually we're going to return games won. Here's a difference, very slight difference. The main difference here is that we've used int64 instead of this completely empty array. So for n games, again, I'm declaring this games won is equal to int64 here. And for 1 through n games, again, doing the same exact thing. And we're going to run both of these values. Okay, so one thing, let's see. Okay, I'm just gonna, okay, so let's look at these numbers for just a second. For the version where we didn't introduce any type or any, we just used an abstract type, the number of the time was, say, 16.6 microseconds here. The number of allocations was so much bigger, and 11.56, the number of the memory size used was much bigger or bigger. So one thing to keep in mind throughout doing these examples, a lot of these examples are really toy examples, and the purpose is really just to demonstrate how things will differ from one instance to other. A lot of times, like things we might want to look at here is, for instance, the number of allocations, or it depends on each time what we're looking at. But in general, keep in mind that these are toy examples, and these could have a more significant impact when you're building a much bigger function. Here I just reran the same exact thing with the interpolation of end trials. I knew here, like, it's not going to make that much big of a difference, just because what we're passing here really, first of all, we're still like here in global scope, but we're really like, I could have encoded the end trials inside the function and just ran it for end trials times. So in this specific case, it's not going to make that much of a difference. The thing that you need to keep in mind is whenever I'm allocating memory, like if I'm allocating memory inside the function at b time, it's just going to run like what is going to be allocated in the function. So that's fine. Okay, so that's one thing to keep in mind. Just to give you an idea of what I defined looks like. When I defined this vector, empty vector here, what this is actually, let's take a look at this. So when I defined H to be the empty vector, it was actually of type array any, and that's the reason it was an abstract type and it was a complete type here. So that's one thing to start with. The next example, moving on to the next example, one thing you will see actually if you're looking up Julia, or like if you're trying to write your very first Julia function, one thing is always repeated, which is avoid global scope. So try to run things in local scope. What's the difference between global and local scope? Anything, for instance, on the REPL, like where we're running here on a REPL, it is of global scope. If we're running things from a function, it is local scope. So what you should usually do is normally just write everything what you need in a function and then just run the function or call the function to test it. So for instance, here we're actually doing a mini sample of that where we're writing a function. We're still playing the same game where we're recording the number of games won, except that here we're declaring the number, we're playing the games ahead of time. So we are, all games is the round of end trials over here. So these are the number of games. And then the games won, we're declaring, now we're switching back to N64 because we know these are the number, the games are going to be numbers and we're storing them here in this vector. And we're doing honestly the same exact thing, except I changed something in the syntax for you just to take just get an idea of different syntaxes of writing the for loop. Current I is just going to be, we're enumerating the number, the all arrays vector in this case. We're not, we're enumerating it, and the way we're enumerating it, calling the enumerate function. And what we'll get in return for each iteration, we're going to get the I index current I and then the actual value. So char game is actually all games of char I. So that's how you might want to see it. Just basically write this here. Okay, and then we're going to return the games won, and then the rest is essentially the same as, yeah, the rest is we're just playing the games, except that here we're playing the game inside the function itself. So let's try this out. So one thing, let me see now, questions. Okay, so people are asking questions, and thanks for everyone who's answering questions. That's amazing. If anyone, Valentine or Mary, if you want me to actually address the questions, just ping me. Thanks for everyone answering questions. That's great. And if you want to ping me, maybe the best way to do it is just to talk or send me a message on Slack. I have Slack on a different device. Okay, so going back here, Great, so we have the number of trial, like we ran the games beforehand and we ran the games inside. And this is the main difference. So here, when we're running in global scope, the number of seconds was 106 microseconds versus 9 microseconds. Huge difference. This is one of the main things you want to remember while you're writing your first Julia code. Again, the only difference we did here is we defined this value function, vector outside versus we defined this vector inside. So just keep in mind that you should do this. Okay, so avoid global scope. One thing here is if you really must use global scope, it is recommended that you use the const. So here's an example of, oh yeah, I do have an example later. Okay, so if you really have to, yes, use the const keyword. What const does is that once you've created something of type const, or not type const, you've declared it as a const, what happens is that you cannot change its type later. And the reason this is good, if you must use global scope, is that the compiler knows its type. So whether you change its value in the future or not, that's not a huge deal. The compiler knows its type. So just an example, because const can be misleading, thinking, oh, it's a constant, I can't change its value. You can change its value, you just can't change its type. So if I declare const of my global int here to be 1, and then my global int is equal to 2 here, and then I change the value. So I'm going to get a warning. It says redefining constant my global int. That's fine. But it worked. I was able to redefine it. While here, if I try to redefine it to 1.5, 1.5 is no longer an integer, where like the original definition was an integer. So now it is a float 64, and I can't actually, this is not a legal assignment. So that's one note about global versus local. Okay, moving on, we're still playing the same game, trying to squeeze even better performance of this game. The next thing we'll cover is pre-allocating memory. So we saw so far, we've been using this keyword, which is the push keyword. So far, our best performance came from this function over here. And we were using the push keyword, or the push function, push bang. Let's revisit it here for a second. Oh, actually, let's revisit it here. Okay, so we're looking here, we've defined the all games played, and for every time it's bigger than or equal to 0.5, we are pushing to this empty vector that we've created and adding this char I over here, adding the game number. So instead here, we're gonna do something slightly different. If you look here, I think, yeah. Okay, so if we're looking here, we are going to, first of all, play the games, get all the games that we need to play. And instead of declaring a vector that is just an empty vector of 0 numbers, I'm just gonna set a heuristic here. I'm just gonna say this games1 vector is no way gonna be more than the number of games we're gonna play. So if we're gonna play 100 games, the games1, there's no way they're gonna be more than 100 games. Since I don't know the output, I don't know how many games will be won. One way you could do it is maybe assign half of them, because again, like here we're playing 50%, so a good chance like 50 might be a fair estimate here. And then if you reach 50, you can just check and then increase the size. But I just wanted to show you one instance of performing this scenario here where you don't know ahead of time how big the vector is. Sometimes you have a fair idea, like if you're working on a problem and you know like it's probably not going to be half of the number of trials, you can set, say, a half of your size of the number of trials. So again, the main component that changed here is this number of trials. And instead of pushing, I'm just here increasing, just setting GI as this counter that is going to go in games1, and I'm setting the values inside games1. Assigning them instead of pushing them. And then this is returning, the return value is just I'm truncating the vector to return just one up till whatever GI I reached last. I'm just subtracting one here because eventually I have one extra index when I leave the for loop. And so let's take a look at how this will look like. So yeah. Yeah, so I guess a fair comparison here, I think so far we've had the local version turn out okay with the push. And again, push here is not too terrible because like, I think there's like just, we're running 1000 instances. At the end of the day, again, these are toy examples and the push can cause problems in the future. Even without, even without like comparing this most recent one, we just like, there's a slight improvement, a couple of microseconds. I don't know if you want to call that an improvement, but that is probably a better way to do it, especially that you're using less allocations here. So one thing you also care about is looking at how many allocations you're making in your system. So fewer allocations is better. All right, so that was it for the previous example. Now I'll move on to the next component, the next example, and that is I'm going to talk about this whole fuss about vectorized versus for loop. So if you're coming from maybe like the MATLAB background, a lot of times like the MATLAB background is just like vectorize everything. You need to vectorize everything. And in Julia, that is not true. For loops are actually pretty efficient. So we will see an example of that while we're covering the broadcast operation or fused vector operations. Let's just take a look. So what I'm doing here, again, we're still playing the same game, but we're, again, squeezing more and more out of the game. This time, we're still playing end trials. We're playing all the games ahead of time. And now the next thing I will do is just do this operation over here, which is all games dot bigger than or equal 0.5. So this is, once I find all the values here, these are actually going to be the games won in this scenario. There are a few things that happen here. I have created the games inside, so local scope. I've put everything in a vector and played the game. All right, so let me run this game. Okay, I actually didn't cover for loops here. Yeah, for loops are just the next example. We'll get to that in a second. So bear with me here. Okay, so yeah, this example was more about the broadcast operation or using fused vector operations. So broadcast is not necessarily the same thing as vectorize, and we'll see that in just the example below. But this is really what we did here is we broadcasted that operation on all the all games vector. And so far, I think this was the best performance we got over here. Here's the example I want to make the distinction about vectorized versus broadcast. So for instance, let's say we have a function here. F of x is just some math function. Y is equal to 3x squared plus 4x plus 7x cubed. You can do one of two things. You can, essentially, I view this as maybe the vectorized version where we're taking every vector, we're using vectorized operations, like all like we're putting everything in the function itself. And we're computing it. Let me just do a different, if I do g of x here. Okay. Sorry, I think I have missed a couple of the previous ones. Anyway, okay, so f of x and g of x, and let's take a look at how this will. Oh. Okay, so let me just describe what's the difference between these two. Both of these are calling the same function f, right, over here. One of them is treating x as a vector. One of them is taking f as a vector and doing as a vector for every element, raising it to the power 2 and so on and so forth. X multiplying it by 4 and raising it to the cube and multiplying by 7 and adding everything. Versus here, f of dot x, what it ended up doing is it broadcasted f to every single element in the vector x itself. So now when I passed f here, when I passed $x to f here, what's actually being passed is the elements themselves. And basically it gets dropped. It's as if this dot over here doesn't exist because now I'm running it on a scalar. It's essentially exactly equivalent to what I have here in the GH function. So without the dot over here. GH is not going to work on the vector x because it's just going to complain. It doesn't know how to do x here. X squared, a vector squared in Julia is not defined. Like it's x squared is not defined. But if you actually want to do the element-wise squaring, you have to do the broadcast operation, which is the dot squared. So f and gh here are equivalent. And as you can see, using this fuse operation, which is passing f as a broadcast on the elements themselves, is actually was better. So this is something to keep in mind. Okay, this is where we get to the vectorized versus not vectorized and for loops. So again here, so here is probably the first time we're switching kind of the examples we're working with. And this time we're going to work with another toy example, but this time the toy example is finding the hypotenuse of the right triangle. So we have the base and height. Just go back maybe many years ago when you were still in school. And you're trying to find the hypotenuse for many triangles where you have the base and height. What I'm doing here is actually similar to what I did in this f function, which I didn't recommend, right? Where I said I'm just going to do the operation inside the function itself. So I'm taking b and h. I'm raising b to the power 2 plus h to the power 2, and then taking a square root. And then I'm doing the same thing, except I'm doing the find hypotenuse of b and h, except that I'm doing a for loop. Really, all I'm doing in terms of difference here is accumulating everything in this pre-allocated vector, Achian vector. Achian vector is equal to similar of b. What it's going to create is just going to create a chunk in memory that is of the similar type or similar structure of b. So it's going to have the same size and it's going to have the same type. So let me just give you an example here. If I have b is equal to rand of 10, and I do this, so Achian vector is of size 10, which is the size, and then element type of b was float 64, so it's created float 64. So this is just a quick and easy way to create a vector of a given type of a given length. Okay, so these are equivalent, except that I'm pre-allocating memory here and storing everything in this vector. So let's see how this will look like. I'm just going to add all of these here. Honestly, yeah. Okay, so we can look at the timings that I already had. One thing to notice right away is the vector. If I compare the vectorized with the for loop, there's about a difference in like half the speed and much fewer allocations. There's only one allocation here. What's happening is like I'm really just allocating this vector in this for loop situation. Versus what I'm doing this, I'm allocating, like first I'm doing, I think what happens in the underhood, there's an allocation that happens here, and I think there's an allocation that happens here, and then a third allocation, and then a fourth allocation. So you probably don't want to do that. For loops are just fine. I would recommend using for loops, or using the fused operation that we discussed just a second ago. And it's actually fused is even better. So like broadcasting here worked. The only difference is the allocations. Like you might want to keep that in mind. But it's also good to know. So I really did, for this function here, find hypotenuse vectorize, it's still using the same function, except that with me passing the dot of b comma h, I'm actually saying, don't treat those as vectors, run find hypotenuse vectorize on the elements of the vectors and not treat the entities as vectors themselves. Really exactly similar to what we did in f and f dot over here. Okay, so yeah, so I mean, honestly, I think if I have to summarize this section with what to use vectorized and vectorized for loop, I'm strongly, almost all, like a lot of times I use this strategy where I'm actually, when I want to write a function that runs on multiple elements in a vector, I just run it, type it as if I'm going to do it on each element, and I just let the broadcast, the fused operation do it. A lot of times it's pretty good, so it's fine. Okay, moving on to the next example, reuse memory. With reuse memory, we have seen something about memory earlier, which is pre-allocating memory. This is going to be similar. And the only difference is that we will end up having to use this memory more than once. So let's just actually look at the example. So the goal here is to find the sum of square roots. So we have a number of elements in a vector, and we want to find the sum of the square roots of these elements. And again, these are a lot of times toy examples. Like, I think if I'm writing it myself, I would just call the broadcast operation. But the goal here is I wanted to just demo one specific thing. So what I did here is I've created the vector that I will actually return. The vector is going to be of type float 64 because I know these are going to be square roots of those numbers, and I'm defining it to be of, so this is the size of the vector and vectors, and then each element is going to be of type float 64. So here's what I'm going to do. Oh yeah, sum of square roots from 1 to I. So yeah, this is what we're doing. So for I is equal to 1 through n vectors. So let's say we have 10 values we want to create. From when I is equal to 1, I'm just going to take the sum of square root of 1 through 1. And when I is equal to 2, I'm just going to take the sum of square root of 1 through 2. So every time I want to use, the first time I used 1 to 1, and then the next time I used 1 to 2, and then the third time I used 1 to 3. So every time I'm using a new vector, what I'm doing here. And we'll see in the next example how we'll do this slightly different, but keep in mind that I have the main vector, but I'm always using, like, recreating 1 through I at each step. In the next example, and then I'm allocating everything in this vector, some vector of I. That's fine. That's pre-allocated. We already covered that. Now, the difference I'm going to do here is I'm actually going to make this a new vector v, which is also of type float 64 here. The way I'm going to do it is, yeah, I'm just trying to remember what I'm doing here. Okay, so the only distinction I have here is instead of creating this 1 through I in memory and just letting just Julia figure out where to store them, I'm just going to allocate some chunk in memory so that I can actually do this operation in it. So I'm creating this v vector. And for each time in this for loop, here's what I'm doing. I'm creating the square root of 1 through I and placing them in 1 through I. So I'm already telling Julia to put, or the compiler to put these values and these pre-allocated spaces in memory that I already created. Now, this might be getting a little kind of convoluted in your head, but the goal here is to tell you that if there's something you're creating at every single for loop or every single function call, let's say, and you're calling the function so many times, bear in mind that maybe it's good to just create that vector, because all I need from that vector is really the sum. So I don't really need to store it. So remember that you could store that memory ahead of time and then do that computation in it. So this is how I'm doing it. I'm assigning 1 through I, and that's the square root of 1 through I. And then I'm doing the same exact thing here. So some vector of I is just the sum of V. I'm resetting everything to be 0 just in case. But actually here it's not going to make that big of a difference, actually, because as you can see, what we're doing is going from 1 through I. So if you haven't touched the last elements, they're still 0. But if you want to be extra careful, you can do that. Notice that I'm setting this V with dot equal. What this means is, again, I'm setting 0 in every element in V rather than setting V as a variable to be 0. And if we look at these, I'm just gonna let's see. So I think if I all right, okay. So if you're looking at the numbers here, the main thing you will see, I mean, the values here are not like that big of a difference, but the two main things you might want to see here are the allocations and the memory used. As you can tell, like the main thing we did here, we've avoided recreating memory over and over and over. So if memory is an issue while you're writing your code, you might be like, you might decide to just pre-allocate the memory ahead of time. Yeah, similar results here. So again, yeah, like it's not that big of a difference, or I mean, there is like 100 microseconds. I guess it might matter sometimes, but again, the key distinction is memory and allocations here. Great. So as long as we're talking about memory, we're still going to work on the same example of summing 1 through I as vectors, square root of those entities, and then summing them, except that now we're going to introduce the @view macro. So what does that @view do? Yeah, I think we'll go back to that example in a second, but I'm introducing it with a different example here. So I'm just using so here's what I'm doing here. I'm creating this random sp-rand, actually a sparse random matrix of size 500 by 500, and the sparsity or the density is going to be 10% or 0.1 here. So we are going to sum some of these values in two different ways. One way is, let's assume you have a certain set of row IDs and column IDs that you want to kind of take a chunk of the memory or chunk of the matrix and take a sum of those specific indices. I'm using a sparse vector matrix here. Honestly, if you use anything, I'm just trying to make it a little more complicated, just because with sparse matrices, like sparse matrices are represented in memory in a really neat way via the compressed sparse column compressed sparse column format in Julia. So like summing them might like be sometimes interesting, I'd say. So that's why. I mean, you can try this with other examples, and we'll actually go back to the previous example and see it. Okay, so really the main difference between the lines here is really this line and this line. This is just a different form of writing it. Instead of calling A of row IDs, column IDs, I'm using a view. What view does is, instead of, if I'm calling A of, say, some indices, some other indices, instead of creating or looking at those as maybe copying them into a new chunk of memory in memory, I'm actually just taking a view in them. I don't want to do anything with them. I don't want to change their values. I don't want to do anything fancy with them. I just want to take their sum. So I might as well just take a view on them rather than copy them. So as you can see here, yeah, the main difference in terms of allocations, 6 allocations, and then way less bytes in contrast to the previous, yeah, both these numbers look the same. Way less bytes and fewer allocations. Again, there's a toy example. We're just using 500 by 500, not that big of a deal. But if you end up having to use, say, like 1,000,000 by 1,000,000, that can get complicated pretty fast. But I'm keeping things simple on my laptop since I'm running like screen sharing and screen recording and so many things. So trying to take it easy on my laptop. Okay, so moving on, we're still going to talk about views, but this time we're just going to remember this example we had here where we're summing 1 through I, except you remember here we took a copy, we have pre-allocated some memory V of 1 through I and took the square root of every element and allocated them in V. What we will do here is instead, yeah, this is the views solution. Okay, yeah, I think I reran the copies solution just to give a contrast. Okay, so let me rerun this. And then I'll rerun this as I describe what happens. So what I'm doing here, remember when oh yeah, okay, so I'm creating here a slightly, again, different solution. And the different solution is instead of recreating square root of 1 through I every single time and allocating it in view 1 through I, which I already pre-created, I'm coming up with a new solution, which is going to be better. And the new solution is, since I know, I mean, one thing in writing optimized code is actually redesign your algorithm. Just think of what you're really trying to do. And one thing I often try to think about is, how can I redesign my algorithm to make the most sense of it? So I know I want at each iteration to go from 1 through I, but I'm going 1 through I and I'm doing it like multiple times. So I might as well just create the square root of 1 through n vectors up front, and then every time just call the sum of v 1 through I. This is really what you might want to do. But as an example here, to compare this scenario to the view scenario, instead of using v of 1 through I, again, there's really nothing fancy that I want to do with this v 1 through I. All I want to do is just take a sum of them. So if I call add view on them, this is really all I need. So here, when I call add view, I'm getting a view onto this vector 1 through I. I've already pre-computed everything. And as you can see, the speed is kind of a factor, an order of magnitude faster, and also much less memory. So that's a good thing. Okay, so moving on, we are at example number 10 now. And we're still in the memory situation, but we will now talk about in-place operations. In-place operations in Julia, what they allow you to do is essentially change something in your input. So let's go back to this example we have already seen before, which is the find hypotenuse of these B and H base and heights vectors. So this is the solution in the vectorized form. And this is the solution in the in-place form. So it's still a for loop, except that now what I'm doing is, let me copy this again and pre-run it as I described it. I'm sorry for, I haven't, like, sometimes I can be sloppy, sorry. Okay. Okay, so what I'm doing here is I'm taking B and H and saying, well, after I find the hypotenuse, the base hypotenuse for these base and heights and the triangles, I'm actually not going to need B and H. So really, I can actually store the values that I want in one of them. Like, I don't need to store to create a new vector in memory and store the values in it. I can just store in either B or H, it doesn't matter. So here I'm choosing to store in B. One thing to note here, I've added this bang operation. In Julia, it is by convention that if you're changing something in the function itself, so like here, as you can see, I'm actually modifying B. you should, by convention, you should add this bang operation so that you know that this function is going to change one of your input vectors or one of your input arrays, for instance, in this case. So here I am changing b. Again, I'm just going to rerun a couple things. I've created b and h and running them. Let's look at the results here. So let's see what happened here. If you remember, we already ran those earlier. So we had vectorized on the vectors themselves, and we have vectorized broadcasted to the b and h. So here we already went from 4 microseconds to almost 1 microsecond, so 906 nanoseconds. And then there was the for loop, which is again 1 point something microseconds. So and then if you remember, I think I said one of my favorite formats was this format. So the new thing that we just introduced is really this final thing over here. This final thing over here. So what we did here instead is allocated 0 memory. So like there's zero allocations and 0 bytes. So depending on what you're trying to do, with like if memory matters more, time matters more, depending on what you're trying to do, it might be maybe feasible to actually use the in-place operations sometimes, because you're really storing no extra memory. So it can be useful a lot of times. Okay, so this was the in-place operations. Okay, so still in the realm of memory management related stuff. We are going to now talk about iterators. So Julia actually provides a really cool infrastructure for creating your own iterators. The reason, or times when iterators come up a lot for me personally, is when I have something of this format. So let's talk about iterators for just a second before we get to the example. So what are creators? What are iterators? We create iterators, iterator objects when we don't want to create all the elements in an array once. So this is really like, this is when I use iterators the most, when I actually don't want to use the values that I'm creating in this function. So here's a quick example to see what I mean with that. So let's say you want to use the Fibonacci sequence numbers for a simple purpose, but you don't necessarily care about storing all of them. So you want to do something like this. You're creating a fib iterator, a fib of n, and now for each element I in this fib iterator, you're doing something on it. I don't know what's the something. You just are going to do something with it on the spot and just get rid of it. Like you're never going to use that value ever again. Similar thing, so in the above iteration, you are not computing and storing all the Fibonacci sequences, sequence numbers. Instead, you are just creating them on the fly, basically. Every time you're using, you're pulling a Fibonacci number, it's just an iterator based on what you have already created previously. A lot of types in Julia are actually iteratable by default. So like when you use a format, something like I and rand of 10, what you're doing is these are just like you're iterating over the vector right away. So rand of 10 is an iteratable vector. So like if I create here v is rand of 10 for I in v at show I. So vectors are iteratable by default. So this is just to give you an example of something that is iteratable in Julia. Now the question is, how do you create your own iterators? So here's an example. So I think, yeah, so what you really need to create your own iterators are really the main chunk of work is going to go in this base.iterate function. So here I'm just creating this struct, which is fib iterator that we will use later. We'll see how we will use it in just a second. Really, the most important chunk of work that's going on here is in this base.iterate function. So we're first of all, iterate is a Julia function. So we're actually overloading the function. We're using a function that already exists in Julia, but we're defining our own inputs on it and using our own inputs. Okay, yeah. So my computer is doing something weird. I can't get a hold of the cursor. Okay, good. Okay, so I'm passing this fib iterator struct that I have defined here, and we'll see how we'll actually use it. And usually when you are running an iterator or the base.iterate function, you have a state. And the state is going to be useful to understand where, when to start, like whenever it's a start state or an end state, or you want to keep going. So for instance, if we start here, so we have usually in Fibonacci, all what you really care about is the previous two numbers, right? Like, so if you have the previous two numbers are 1 and 1, you know that the next number is 2. So the first thing I'm going to do is I've defined the state to be actually a tuple of 3 things. The 3 things are the previous 0, 0, 1. So previous step ID. This is going to be the state. And then I'm going to say that its step ID is equal to 1. So I'm just starting. The first values are going to be 0, 1, 2. And as long as f of f dot n, which is this number, so we want, let's say we want to run the Fibonacci for 10 times. So f dot 10, the value itself is still haven't reached the step ID. So this is really just the index of how many times we've run the Fibonacci iterator. As long as it's less than step ID, it's fine. We're going to keep going. And so this was for the first state. This was for the continuing state. And as long as it's continuing, here's what will happen. Y is equal to previous 1 plus previous 2. And then the step ID is incremented. And then what's returned is now a few different things. So what's returned here is Y and previous 2, which was the next number over here, and Y, which was the new created number here, and then step ID, which was the incremented value here. So really what you care about, what we're looking at here is these values that what we are returning. I'm trying to see something. Yeah, so the actual values themselves are actually the Y values. So as you can see here, I have Y, I have, sorry, this was the first number, Y, 1, and then Y is created here, and then I'm returning Y over here. So this tuple of 3 things, all what it is serving is for the iterator to know where I am at this point. Because all I want to look at is the state. So I want to look at the previous state, which is previous 1, previous 2 step ID. So when you're creating your own iterator, you want to keep in mind that this state you have is what will determine the next value in your computation. So there's this distinction. There's the state and what you're actually returning. In this case, it's the Y value. And I know I'm probably glossing over some of the details here. There's probably more. I can try and find you more resources online to try and find, or I mean, the documentation can tell you more about how to do the iterators. But again, like keep in mind, there's the difference between a state and what you're returning. I'll just like take a step backwards and go back to the real goal of this workshop / this example, and that is to show you one way to save on memory in this specific scenario, and that is you can create iterators, and all you really need to define is this base.iterate function. We will now just talk about this other form, which is just a standard way of doing my Fibonacci via an iterative method. Just an iterative algorithm. So here we have the n that we're interested in. We are pre-allocated. We're saying we're going to have zeros of this time. It's going to be everything we have in, since they're Fibonacci numbers, they're integers. I'm just going to use int. And then for the first 2 numbers, I'm going to set them to be 1 and 1. And for everything else, I'm just going to add everything that was before them. Just tempered Fibonacci. Sorry. Okay, so now we're actually going to test these two things. This is the fib iterator. Yeah, so let's see what happens here. Okay, so here's the main difference. Okay, so we have this test allocate. What test allocate does is for every time, this is the my fib of n. So my fib of n is now essentially every time I'm calling it on n, it's creating those values. So for I is equal in my fib of n, this is really the vector that gets returned my fib of n. There's the return v, so this is the function. This is really similar to if I write v is equal to my fib of n. Sorry, this may have been a little confusing. Let's run it again. Yeah, similar. Okay. So yeah, what we're creating here is we're using this v vector and we're iterating, we're going over every element in the v vector that was allocated in memory, and we're adding the values again. We're just creating a sum of these first and Fibonacci numbers. In contrast, what I'm doing here is I'm saying f is equal to fib iterator of n, which I already defined over here. So fib iterator is here. And since, so this might look like magic to you, but it's not. And the reason is what I did here is I only called, I created this f is equal to fib iterator of n. So like I created, I'm saying I want 10 numbers, let's say. And because I'm putting it in something that is iteratable, so it's a for loop I in f, what's happening here is that it's immediately calling that iterate function. And because it's immediately calling that iterate function, and I already have what the state start is, like I already have declared what the original first state is going to be, it immediately going to call this function because I'm putting it in a for loop, because I'm saying for I in f. So this struct has been, iterate function has been defined on the struct. And now it's going to do everything else based on the state. So like the first time it was going to be 0, 0, 1, but everything else, everything is actually changing. The state is changing, the previous's are changing. So yeah, like previous and step ID are changing. So the state is changing. So every time it's repeating, it's taking a new state in. So I know that it kind of might look like magic, but it's not. It's actually just calling, since I know that there's an iterate function defined over f, it's going to work. Wrapping up this part, this is what the reason I went in this direction of iterators is to show you one example where things, when you actually don't need the data, you just want to do something with the value itself. Like I just want to add the first 10 Fibonacci numbers together, and I don't want to use any of them later. I can just create this iterator function, and on the spot, I'm just going to create an iterator value. I'm accumulating them in this S number, and I'm just adding them, and I'm never going to use them again, so I don't need them. So kind of an interesting distinction happens for the test iterator. It's so it's about an order of magnitude difference faster, and again 0 bytes, because I'm not really allocating anything. Actually, yeah, I'm not sure why. I feel like this might. Anyway, I think the key thing I wanted to show here is the timing difference. I'm kind of reluctant to say there was nothing allocated here, but I'll skip that and not think too much about it for now. Okay. Moving on to memory and matrices. If anyone in the chat in the panel has any comments on this, I'd love to hear. I'm kind of a little reluctant to say this is, or maybe I'm not sure if I did something wrong here, but I don't think I did. Yeah, I think this should be fine. I think this is probably correct. Okay, so moving on to memory and accessing matrices in Julia. So let's see what happens here. The key thing I wanted to say here is sometimes, yes, you have, say, a matrix of size m by n, some number of rows and some number of columns. Yes, it looks two-dimensional in visual space and plotting it or visualizing it on a computer. But in memory, it's really just a one-dimensional space. This is how it's actually stored. So let's run this again as we're talking. Okay, so we have three examples here. We are going to accumulate the sum of these values in this matrix over in three directions. The first direction is over the rows. So we're going to take the m and n sizes of size of A, and then we're going to fix the row and loop over the columns. So for each row, we have the row fixed, and we run over the columns. The next way is to fix the column. In this case, we're fixing j is equal to 1 through m, and then we're running I is equal to 1 through m. So we're looping over the row. So we're fixing one column and going through the elements in that column. And then finally, it's true. It's true that we have a two-dimensional matrix. But as I said again, actually this matrix is stored in memory in one dimension. So actually you can very easily access the one-dimensional space of this or the one-dimensional indexed version of this matrix by just essentially, instead of looping from 1 through m, I from 1 through m and j from 1 through m, you can just loop from 1 through m times n. And this is going to work just fine. The linear indices are going to be mapped from 1 to m times n. My sum is just going to be the addition. So three things have happened here. So let's look at the run over here. When I ran it with rows, ran it with columns, and ran it with indices. Index. Oh, I see what. Oh, yeah. Okay. Okay. So what happened in the first time? I'm actually, instead of when I'm looking at each row, you're not really just grabbing one row in memory and looking at its sum. You're actually grabbing more than one row to be able to look at its sum, because like memory is actually assigned in column wise and Julia. So what ends up happening is you're going through the columns, but you're looking for, if you're grabbing a cache from memory, you're actually grabbing more than, for instance, here, if you want to grab like the cache size is 8 numbers for float 64, you're grabbing more than 8 to be able to just come up with the summation of the first row, for instance. Versus when you're doing things in column wise, every cache line you're grabbing, it's actually just useful because you're taking it, using it, summing everything, and then every time you're getting another cache line, you're using it again and using it, all of it. You don't have to grab it a second time. That's it, like you're done with it. So moving via columns or moving via indices is very similar. These are similar numbers. If you're using a linear index, is just as fast or even faster, actually. But the key thing to know here is to not access the matrix via rows first, access them via columns. Just keep that in mind. Okay. So we've talked about memory quite a bit. We are going to go now to one of Julia's most interesting, or if you write your first Julia code, a lot of times you will see one of the first things you will see is write type stable code. So this is what type stable code means. Let's actually start with an example. We're gonna just have this quick game here where what we're saying is 0 or val. There's two functions. There's a stable version and non-stable version. And the difference here is, sorry, the goal we're doing here is we're passing a vector, a value x. And if x is bigger than or equal to 0, we are going to return x itself. And if x is smaller than 0, we're just going to return 0. So if you actually look at the code here, it looks fine, right? We're passing x. If x is bigger than or equal to 0, we're going to return x, else we're going to return 0. So far, so good. except that there's something that's going to be problematic. And the problematic aspect is, let's actually run this code here. Okay, so actually there, I haven't introduced code warn type yet. So one way in Julia to be able to see if your code is type stable, and again, type stability is an important issue in Julia. You always want to make sure that your code is stable. To be able to recognize whether your code is code stable or not, I recommend using this macro code warn type. That essentially, usually, if there's something that is not code stable, it'll color code things. So like if you have a red text in your output code warn type, it means that your code is not stable. So what happened here? Why is this code not code stable? This is what happened. So if let me just grab it. Oh, it's here. Perfect. Okay, so this is my indication that it's not code stable. And then if I look at the stable version, I don't have any colored or red colored text. So the difference, what happened here is when I pass this 0.2, the return type, when I'm passing, forget about the 0.2 for a second. What I know about 0.2 is that it's a float 64, right? Like when code warn type is running, it's not actually looking at the 0.2 itself. It's actually looking at the type. It's a type float 64. So when I pass a float 64 to this function over here, there are two scenarios. If it was bigger than 0, it's going to return the number itself. And if it returns the number itself, it's going to be of type float 64. But if it wasn't bigger than or equal to 0, it's going to return 0, which means this is an integer. The way I'm defining it is an integer. So depending on the value, it might return a float 64 or an int 64, for instance, here. But what I'm passing is still a float 64. So the question in type stability is, given a certain type as an input, can I predict what the output type is? And if I tell you here, I'm giving you this function, and I ask you, I'm going to pass a float 64 type to this function. Can you predict what the output type is? And the answer is no, it's either going to be an N64 or float 64. We don't know. But if you look at this code over here, I'm passing X and I'm saying, I'm going to pass a float 64. Do you know what the type of the output is going to be? And the answer in this case is yes, because if X is bigger than or equal to 0, I know I'm returning X, which is the same type we started with. That's a float 64. And if we're returning the second branch of the if statement, it's going to be 0 of that type of X. So it's 0 here as a function. We're using 0 as a function, and we're declaring this 0 to be of type, whatever type X was. So 0 of type of. And we'll see different samples of how you can do this in the next couple of examples. Okay, so moving on. Yeah, so type stability is about that question. Can I predict what the type is? Let's look at this quick example here. So I'm revisiting type stability here with a little more details and a little more hints on how to fix some of these issues with like zeros and like the 0 that I had here. Okay, so here what I'm doing is I'm using this v, I'm square plus 1. I'm just taking g is equal to v times v and then returning g plus 1. And the question is this type stable? And the answer is yes. The reason it is type stable is, let's look, we have some, yeah, let's look at this text written here. So when I'm passing v and it's v is of type t, when I'm multiplying something of type t times something of type t, I know that the type is going to be of type t. And then when I'm returning a value plus, for instance, here is a type state, like for float 64. If I'm passing float 64 plus an integer, actually what's going to happen is the addition of a float 64 and an integer is gonna promote the type, and it's not like we know that addition of a float 64 plus an integer is going to be a float 64. So for instance, here, if I actually do like 1.0 plus 1, the answer is 2.0. And the reason is, even though like this is really just a number, an integer 1, but it's declared as a 1.0, which means it's a float 64, and I'm adding it to another int 64, I know that the value is going to be float 64. So like kind of the max in quotations, but max is probably not a great word to use here. But the point being is, when I added a float 64 and an integer, I know the answer is going to be a float 64. This is one more example of a function that is not typed, or is this type stable? Oh yeah, I see what's happening here. Okay, so let's look at this function and maybe take a look at it and think of whether this is type stable or not. Maybe let's look at the chat box. Let's see if people think this is type stable. If I'm given it's a float 64, do I know what the type is of the output? And if I'm giving it an int 64, do I know what the type of the output is? Just as a hint, not type stable. I have people saying not type stable. Yeah, that's a good question. If int 8, I don't think that's actually, yeah, that might, let me think. Yeah, that will still work. uint is going to work, because let me double check that it will work. I'm not sure. Like I'm doing something wrong here. I can't see the chat box either. Yeah, that's what I was going to say. uint of type 8 plus 1 is going to promote. That's the key thing. That's yeah. So if it is like of type less than or smaller, like something smaller than int 64, it's going to promote to int 64. And if it's in general, addition will know what the bigger type is going to be, what the promotion will happen to. So yeah. Anyway, I'm not sure. I feel like I typed something wrong here, but I'll skip that for now. And I looked at the chat. Looks like a lot of people are saying it's not type stable, and that's true, because if I actually pass this with an integer 2, it's not going to be stable. And the reason it's not is, say I'm passing 2, and then this is the modulo function. So it is an even number, and it's going to go here. But even though I divided by 2 is, we know we're going into a branch that will be I is an even number, and even divided by 2 is going to be a whole number. This is still going to return a type float, and that's because the division, this function, the way we're is going to return a float 64. Even if I'm dividing integer by integer, so integer over integer is going to be a float 64. The way to do it, if I want to fix this, I would do div of I, 2, and this will fix things. So what the div function does is, if I'm doing div of 10, 3, it's going to return 3, which is I think it's the whole, like I forgot what is the technical math word for it. Any help on the chat? No. Okay. Yeah, it's just like the integer part of
integer division.
Integer division. Yeah. Okay. Yeah, the whole part of dividing, integer division of dividing 10 by 3. Yes. So you always get an integer with a division. This is how we fixed it, and now this function is type stable. Okay, so I'm wrapping up the type stability aspect. I did mention earlier, I did want to show you other ways to, for instance, fix this problem here when I said 0 of type of X. There are a couple things you might want to know about, random things. One instance is I'm back to the same example where I'm saying 0 or val. So if the number is bigger than or equal to 0, I want to return the value itself. And if it's smaller, we're going to return 0. So one way to do it is to promote type. So you can promote the type of X and int. That way you guarantee, since 0 is of type int, so I'm promoting the type of whatever X was and the type of 0 really, which is an int actually. So I'm promoting both types and getting whatever type works for both of them. So this way, whatever I'm passing, it's just going to work t of X or t of 0. One other way is I can annotate. So I can just enforce 0 to be of type of X. I can also, if I'm passing, if it's parameterized, if X, I'm passing a value X where X I'm saying is of type T, or T is something in the subtree of real. I know I'm parameterizing it, so I can return T of X. So I already have the value T, the type T here. Other ways is I think we already did 0 type of X. One other way is to actually call 0 of X. So 0 of X is just going to be return a 0 that is of the type of X. We can convert. I think convert does the right thing, right? Yeah, you can convert to, let's actually double check. I'm not sure. Yeah. Yeah, so these are just running through some examples of other ways to, if you ever want to promote types or change types based on what you have. Okay, so moving on, yeah, so all of these are going to turn out, oh, I don't have, okay, yeah, all of these are going to turn out type stable. One more type stability, let's see how many, I keep saying one more type stability and it's like 10 more. Okay, really one more this time. Just because type stability is a really important issue to know about in Julia, and it's always good to have your code type stable. So you may remember from earlier when we wanted to sum the values of the matrix A, and the issue there was whether we're going by columns or whether we're going by rows. And the focus here is now we've fixed things to go by index, so like essentially everything in column wise. And if you remember, we had this MySum value, which had these yeah, the MySum had, we're basically accumulating everything in elements of A of I and the MySum value. And if we actually, so this is just running, getting the code from the top. If I run code warn type here, we're going to see kind of like a bunch of unhappy things. The reason we're saying unhappy things is because of this definition of the 0 here. So imagine first if A was size 0 by 0. What's going to happen is we're never going to go into the for loop, and the integer, the type is going to be 0. So my sum is going to be of type 0. So one way usually to fix this is if it's parameterized, so like I know it's an array t, 2, and say t here is less than or equal to real or number. We can just use the type t. So we already know it's parameterized here. But if I don't have A, let's just like not have anything. So oh, this is still not okay. Go back to what I had earlier. I think I can't think of something off the top of my head. Maybe I'll think more about this example in the break and get back to it. I just don't want to.
Huda, what are you concerned about?
Yeah.
The union nothing?
No, not the union nothing. The union nothing is fine, right? What I'm concerned about is why is this not type stable? Oh, what? I just ran it a sec. Okay, maybe I ran the wrong thing. Okay, good. Okay, then this is type stable as I would expect it to be. Okay, cool.
Wait a second. Go up to the code again. This version isn't. The T is not defined.
Oh, right. Oh, yeah, this is what I ran and wasn't type stable. Yeah, this is, well, okay, this is type stable too. Like, I'm really confused right now. I literally just ran it a second ago and it wasn't type stable. Okay, well, I probably ran the wrong thing. I do expect this to be type stable. Right, Valentin?
Yes, I would also. And it should be 0 of L type A for my sum equals.
Oh my God.
So that's.
Okay, this is still type stable. Okay.
I'm very confused, but
yeah,
Julia is also
I
getting
just have to
smart.
go back. Yeah, I just have to go back to the recording and see what happened and understand what's going on here. But anyway,
wondering
wrapping up this.
Because the other function you previously defined had perhaps a more specific type signature that was being used instead of this one.
Sorry, can you say that one more time?
Yeah, because previously it had a more specific type signature on A, and I'm wondering if because that's still around in memory, that was used instead.
Yeah, dispatch to the most specific method instance.
Ah, yeah, I see. Yeah, so let's just call it something else. Or I mean, this is fine now. For whoever is watching and is slightly confused of what this conversation just now happening, what was it about? So if I had already defined a function that was specific on a certain type earlier, it's still defined in global scope. So like when I ran my function, if it's special, if I already have a specialized function for whatever type I'm running, it might go back and look for whatever I already had defined earlier. So this is what the conversation was just about now. But suffice it to say, and to wrap up this confusion here, what matters is the difference between a 0 of L type versus a 0. Again. Okay, I'm really confused with this example. I think I should just like keep going. I'll try to, we'll discuss this in the break, and if there's anything to talk about, I'll come back to it after the break. Key thing is 0 of L type is going to specify the type of the sum we're accumulating in, and 0 itself is just going to be an integer. So imagine that the size is actually 0. It's not going to be happy. It's going to return the type to be integer, for instance. Okay, so moving on from that example, and hopefully if there's anything weird that went on here, I'll come back to it after the break. Okay, so example, we're at number 15, doing okay on typing. Avoid fields with abstract types. So now we're gonna go to the scenario where we are creating our own types. So it's not about the functions at this point, it's more about creating our own types. Let's say we wanna create this type 1 cube, and the cube is going to have a length, width, and height. So the volume of a cube is c.length times c.width times c.height. So c is of type 1 cube here. The next thing we are doing is passing 1 cube as a real. So not as a real. So we're just naming it 1 cube underscore real. But what we're saying here is the length, width, and height are going to be of types real. So remember when we started this notebook, we said that real is abstract type. So remember that. And now we're just going to define the same volume function on 1 cube real, which is c.length times width times height. And finally, we're going to parameterize And the way we're going to parameterize is, again, we're defining a new name of this type. And then T is here going to be, if I do show type tree of real. So I'm saying T is parameterized to this less than notation column. So really any number, any concrete value of these types is going to be okay when I work with this type. And then I'm again defining the same volume function, length, width times height. And finally, I am creating these 3 cubes, each in a different type. And I'm just making sure here that they are equal. And let's look at this. Okay. Yeah, okay. So there are 2 things, or mainly one thing that I really want to show you. You might look here and say, well, now I have a type on this 1 cube, which is real. That should be specialized. That's maybe good. But really, this form and this form are pretty similar. There wasn't anything much of a difference between these 2 examples, 1 and 2 here. What really was different is this example. And even though you might look and think, oh, like, are these 2 things the same? They are not really, and we'll see why in a second. One thing to remember is this real is an abstract, and every type T here is going to be a concrete type. It's just something in the subtree of real. And as you can see, actually, the difference is quick to notice between getting the volume of the C2S 1 cube real and the parametric version. There's a reason for that. So let's look at these types. When I look at the type of C1, type of C2, type of C3, we are one case we're going to get 1 cube real and 1 cube parametric type. Now, the key thing to distinguish here or see is that we actually also got this float 64 with the 3rd cube. So when I defined this 3rd cube, I know that my 3rd cube has the values in it are actually their type float 64. So when I'm, for instance, here, let me show you one thing. What will end up happening is if I'm working with C2, remember C2 was of this type real. If I change C2 to be C2.height is equal to 1, and the reason we can do that is these are mutable structs. If they are just structs, we probably can't do that. But again, so we're doing C2.height is equal to 1, and I'm going to show the type of C2.height, and I'm going to do the same thing. I'm going to change the C3, which is the parametrized version, to have a height equals to 1. And then I'm going to show the type of it. Now, the type is float 64. Why was that float 64? It was just essentially promoted to float 64. So like if I actually see here, so if you can see, what I ended up with here is this 1.1, 1.2, and 1. And if I do C3 here, I'm ending up with the same value, except that now I know it's parameterized. I know that the values are of type float inside the parameterized version, and this will actually be very helpful for the compiler. So quickly here, also one thing to know is that both of the first versions are actually type unstable, since we already now know that term. And then the 3rd one is actually type stable. So keep in mind, abstract types, if you want to use them, they're really not adding so much. If you're going to the any situation, that's be fine if that's what you want. But know that when you use abstract types, it's not like you're adding anything special. If you really want to use types, either use concrete types in the definition, or parameterized types are just as good. Parameterized, defining types as parameterized types. like this here. Okay, so moving on from this example, running abstract types in definitions. Oh, okay, so we have a quick follow-up here, which I might skip. It does deliver a similar purpose, except that now I'm passing it to a function. This is parameterized versus this is declaring a value of type real and passing it as a vector. So it's really serving the same purpose. One of those is also going to be type stable, and the other one will be over here. Okay, so I'll move on from that example. Everything else is serving the same purpose. Okay, so this is going back to memory, and we've actually discussed something similar in the past about this idea of reallocating memory. So what we discussed in the past was just pre-allocating memory, which is like if I have a function and I'm going to use a vector more than once, just pre-allocate the memory. In this case, what I'm doing is I'm using 3 different functions. And again, this only serves the purpose of a toy example. And what I'm doing here is I'm going to pass sorry. I'm going to pass a number n, and I'm just going to create some random values. And so here's what, so I'm passing a random number n, and I'm pre-allocating memory here, this is the purpose I'm trying to avoid in this example. So I'm pre-allocating memory, and for every time I'm running a rand function, I'm asking, is it above or equal to 0.5? And the answer is yes. It's going to execute this branch over here. And if the answer is no, it's going to do nothing. This is really, again, just to show you like one example of how to do this in one line. This really translates to if rand is bigger than or equal to 0.5, do v of I is equal to 1, else nothing. This is like this line really translates to this line, but we'll stick with a simple one line. And eventually we're going to return v. And same thing, we'll do the quarter situation. We'll take it if it's bigger than or equal to 0.25, and we're going to have a value of 1. Otherwise, this is nothing. And similar thing for 3/4, 0.75. And as you can maybe guess, what I'm trying to do here is I'm just trying to see a statistical distribution of randomly generated vectors. So here I have, I'm taking f median of n. So what this function is going to do, I'm going to create this vector v, and every time it's bigger than 0.5, it's going to allocate a value 1. And the mean here is just going to take however many of them I was able to get to, sum all of them and divide by the total. Same thing with quarters, same thing with 3/4. And I'm just going to return f1, f2, and f3. As you can maybe guess, these values should be close to median, or because we're using we're using the rand function. So it's either, so all the numbers we're going to get are between 0 and 1. So if we run 1,000 iterations of that and we grab numbers of them, the median is most likely going to be around 0.5, and the quartiles 0.25 and 0.75 are going to be around the same numbers. So this sounds about right, especially I'm running it for only 1,000 times. Now, what you have probably noticed here is that I've created this vector v over here, vector v over here, and then vector v here. And then I'm calling all the functions in this main function statistical distribution here. So one thing you can do is, instead of actually creating this v vector in every function, you could actually pre-allocate this vector v. So here, what I'm doing is I'm setting this v vector to be integer of 64, n, and that's the number of times, like it's either going to be 1 or 0. And well, I can actually do booleans here, but I'll leave it as it is, just because now I know it's 0 or 1, right? But I think I messed that while I'm writing this example. Again, the goal is to pre-allocate memory, so let's just keep focused on that. So f1 is going to be the median, and now I'm passing v as an input to the function. Again, I'm just resetting v and then passing it again, and then passing it a third time. So I'm just pre-allocated everything ahead of time and then passed everything. I think the example might be self-explanatory. And again, we get numbers very similar. The difference here in terms of timing will be, the main thing that will happen is that one version is going to have way less memory. Yes. So the version of predefined v is much less memory than what we used over here. In terms of timing, I'd say, yeah, they're very similar. Though I would take this timing with a little bit of a grain of salt, because again, it's a very silly example, and I don't think it illustrates what exactly is going on in terms of the time, but it does illustrate what's going on in terms of memory. So imagine having way more vectors, way more times you're calling multiple functions. This might actually pay off, and you're saving a lot of memory. Okay, so getting close to the end, using multiple dispatch instead of multiple conditionals. So this is more of a, like, I don't think this is like a example specifically for comparisons. This is really just to tell you, like, multiple dispatch actually works and you can rely on it in Julia. So I'm just here, what I'm doing is I'm creating these two types, completely different geometrical shapes, square and circle. One of them is going to have the length and width, and one of them is just going to have the radius. And then I'm going to define this area function, but I'm appending like no dispatch to it. What that means is, like, what I'm doing here is I'm going to check every time, is a geometric shape of type square, and if it is, call a certain function to return the area, and if it's of type circle, return something else and return error invalid argument. Like, you can do it this way, but why bother? You can do it very easily and very simply in this way. You can just use multiple dispatch, and that, I mean, you can create area of C of type circle and just return pi times c dot radius to the power 2, and same thing with square. I think there won't be that big of a difference here. Yeah, it's really just a very silly example. We're only running it also once on just a small circle example. The time, yeah, I wouldn't rely too much on the time here. Yeah, if these were way more numbers, I think the difference would have been way more stark. But the key thing to remember is that actually multiple dispatch works. Like, it's returning, even with a very small example, like these are nanoseconds, not even microseconds. So the just like 0.4 nanoseconds is really nothing. Yeah, I'm kind of now, I regret having a silly example here, but yeah.
Huda, what's happening is that you get constant propagation. And so the circle 2 just propagates into the area, no dispatch. So you need to put it into a ref and get it out of a ref again, which is annoying.
Right. Yeah.
Just
so like
the whole,
dollar,
yeah.
Like this, right? Is that
no. Then yes, square and one pair of parentheses n.
Is that it?
I think before the square brackets, you need one closing parentheses.
Correct. Yes.
And then,
yeah. So okay, so we're having circle of 2, and then ref.
And now do the same thing for the no dispatch.
Oh yeah, I see what's happening. Yeah, exactly.
Still not. Still
yeah,
weird.
I don't think this is, yeah, the thing is, I don't think this is a great example to show that one of them is going to be faster, just because like it's a really tiny example, right?
No, you also have the other issue that it will specialize on the type, and then the isert check will actually just optimize out to nothing.
Sorry, say that one more time.
So if you look at code typed of area no dispatch for and passing in a circle, you will see that the branches actually disappear because Julia is too damn smart.
Okay, actually, let me go back for a second. I guess the reason I think I didn't actually do a really complicated version here is because the if branches actually work fine. Let me backtrack for a second and say if branches work fine. But the key thing to remember is that multiple dispatch is just as good. So why bother write something this kind of annoying versus when you can write something this simple? If I want to wrap up this example, this is really the point I would say here. And yeah, Valentin, you're one of the authors of BenchmarkTools, right?
Yes, one of the maintainers.
Okay, one of the maintainers, right? So yeah, thanks for the great package. But yeah, and then Julia's compiler is pretty good, and Julia is really good. So if the branches will disappear, that's true. Again, the point here is to say you really don't need to worry about branches in terms of writing code. Multiple dispatch actually works, and you can just do it this way.
Uda, could you briefly talk about what ref does, since we've been introduced to syntax?
Yes. I think Valentin might be able to help with this even more. I think what ref, I'm trying to remember. Valentin, do you want to pitch in? Yeah, go ahead.
So every time you get a measurement that is under 2 nanoseconds, you are no longer measuring anything. And that is because the computer is too fast. And if you look at the code, the compiler just optimized it out and figured out what you want trying to do and just returns you the singular answer. And so what happens with a ref is a memory cell. And so you're putting it into memory. And then inside the benchmark, you dereferencing it once and you load it. And you actually, you're telling the compiler, you are not allowed to know what precise value I have here. So you need to actually do some work.
Right. Yeah. Thanks for the clarification, Valentin. Yeah, if you ever have something, if you ever run B time at B time and it has it's less than 1 or 2 nanoseconds, I think this is a very useful trick usually to do. And again, wrapping up, dispatch just works. You don't have to worry about writing branches in code that has branches. Okay, so 18. Let's see. Okay, I think we're fine on time. So this example is about static vectors. So static vectors is, there's actually this package in Julia called static arrays, where basically the distinction between a static vector and just like the standard vector we've been seeing or you've seen in the past is a static array or a static vector, we already know the size of the vector. So a lot of times things can be optimized faster for static vectors. So here I have an example where I am deciding on, I'm creating types for cars. So I'm doing this distinction between mutable car and immutable car, and you'll see it's not going to be that big of a difference here. You should pick mutable or immutable really based on whether you want the fields in your type to be changing or to not allow them to change. Really, that's the main distinction here. But what I want to have is this description vector that will allocate. I think I wanted to do the year and then the number of miles on the car and how many previous owners it has. So what year it was made, the number of miles, and the number of previous owners. So one way to do it is to actually create this description vector, or I could actually create this S vector. That is, I'm assigning it to be here of type 3. So I'm using this static arrays vector package, and the types inside the vector are going to be of types integer. So if I run this, I've just defined the types, And I'm just going to test them. Test every time, test mutable. I'm going to create some random values and call the car a name. And I guess I'm running it for 1,000 times. So I'm just testing mutable, testing immutable, and testing as vector. And then I'm just going to time all of them. And as you will see in a second, what will happen is test as vectors will actually be the fastest here. Yeah, the chat. Oh. Okay, cool, great. Okay, yeah, so as you can see, test as vector is 22.5 microseconds. So like it's about half this, half the speed of test immutable and mutable. So if you actually know that a certain vector is just going to be of a certain size, just set it to be a certain size, use S vectors. That's another trick, handy trick to use. And then finally, in the next 5 to 7 minutes, really what I want to discuss is just a couple of things you might, that might be handy, but also handle with caution or handle with care. I'm going to introduce these macros, but to be honest, like Julia is actually pretty good about realizing when to use these or not. Like Julia's compilers are already pretty good. So like, I think with time, I'm starting to notice that I need these macros less and less, but I will just introduce them here and not go into too much into details. And then in case you know what you're doing and you understand what the macros are all about and you want to dig deeper into them. So there's the inbounds macro where essentially with inbounds you usually Julia, when you're running, say like when I'm calling a of I, actually we are checking that a of I is in bounds. It's in the same, so I is in the boundary of like if it's the length 1 through length of A, it is in 1 through length of A. So usually Julia checks for bounds. If you know that you are within bounds, so like you're going for I is equal to 1 through length of A, you can add the @inbounds macro and it'll work probably faster. But if you mess up for any reason, you're going to get the wrong answer. And debugging this is going to be really annoying. So again, handle with caution. Fast math is really, I think the reason what fast math is used for a lot of, like sometimes in IEEE notation, there are certain things that are done in a certain way. I think I have an example later when I'm adding, see where, yeah, I'm adding this global value XX, I plus XX plus 4. If I'm not using fast math, it's actually following IEEE notation. If I'm using fast math, it's going to do XX plus 4 is going to be added automatically. Again, if you really know what you're doing here, maybe you can use fast math. Just make sure fast math could sometimes, like I would rely on the accuracy of the results in the non-fast math version. But if you know what you're doing, again, this is a macro that you could possibly use. Other macros, there's the inline macro where essentially what the inline does is, I think I also have an example about it here. Yeah, so I'm defining an @inline f of x, y, g, and then typing code typed where I get the type parsed code of G. And as you can see, okay, so I'm going to do 2 versions. There's the no inline version here, and I'm doing the same exact thing, and then code type of G2 of 1. So same thing, this is G, except that it's calling an @inline, this is calling a note no inline. As you can see, there's one less line here. The reason there's one less line is that it's inlined the code type of F inside this code over here. If you want to see the code type of F, it's actually I don't know, actually. anyway, suffice it to say, what's happening is that the code type of the code of F is actually getting inline. It's as if it's like I'm copying and pasting it in it. So it's as if I have this really over here, just replacing the X and the twos, the X and the two. Inline is actually, like, Julia is also pretty good about deciding when to use inline. So again, I wouldn't worry too much about inlining, unless if it's like a really big function that you want to enforce that it's being inlined. But usually inline is probably, across all of these, I think inline is probably one, like Julia is pretty good about knowing when to inline and what not to inline. But it's good to have these tools. Like, it's good to know that they exist if you ever need to use them. Normally, I would recommend writing your own code without macros at first, just to without inline, inbounds, all these things I just introduced, just to make sure that you actually have your code up and running just fine. And as I said, like with inbounds, for instance, like if you mess up, it's just not going to notify you that you have something wrong, and you might have the wrong results. And then finally, I will move to the last item here, which is, again, it's a tools item. If you want to see the low-level versions of your code, if you're interested to know what's going on, one thing about Julia is that you actually can see, yeah. So this is, for instance, this is the same code that I have here, my add one of X. So you can see the versions that the code goes through throughout compilation until it reaches machine code. So it can be handy a lot of times. As you saw, I actually used the code typed multiple times. I also use the code warn type. So the difference between code typed and code warn type, like warn type is the macro to use to know when something is not type stable. It's helpful to yeah, it has this color coding and stuff. So like it's usually good to use, let me type it here, add code warn type. And then code typed, we've just used code typed just a second ago. Lowered LLVM, this is the optimized LLVM code, and then finally the machine code. So these are the 4 macros you could use to generate these codes. And then there's the warn type as an addition. And with that, I think this is a good time to take a break. Maybe we can be back at 9:30 PST. I don't know what that is exactly in all the different time zones, but that's in 14 minutes. So maybe we can take a 14 minutes break and then be back here in, yeah, 14 minutes. Oh, 16:30 UTC. Thank you for Tiago. Yes, I can add the slides to the notebook. I don't have it there. Okay, I will do that right now. Also, if people are asking if I will upload the changes, yes, I will upload the changes. Let me just upload the presentation for now. Is the Slack channel for this workshop listed anywhere? Feel free to create a Slack channel and send it I'll create a Slack channel after this if you don't create it in time. I'll just upload the files first. Okay, if anyone is still here, I just uploaded the presentation to the same GitHub repo. Okay, so I think we will go ahead and get started in maybe just 1 more minute. Okay, so I'll go back to screen sharing. Welcome back, everyone. Okay, so I will actually just kind of wrap up from the previous section and move on to the next section with just a quick couple minutes kind of flow chart of how I process or how I go about writing my own code. Don't take this as a like golden rule or anything. This is really my own personal practices. You're welcome to use it, just sharing it with you. So usually I often really just start, like, make sure you start with a working solution. Depending, I'm kind of obsessed with type stability. Like, I don't like my code to be type unstable. So like I would maybe swap these two things, or like these kind of go hand in hand. Even if the code, or I mean, it depends on, like, if I'm writing like a 2-line function to just something, that's probably not a big deal. If I'm writing like a function that matters, where I am working for a big project or something like that. Oh, I just noticed, is my oh, never mind. Okay, sorry. Yeah. Okay. Yeah, if I'm working for a big project or something like that, it's always good to have codes table code. So yeah, so one thing is I started with benchmarking if the speed or memory should be better, fewer allocations or faster speed, or fewer memory allocated. I first check for code stability usually. I often also check for code stability even before that. So code stable, if the answer is yes, I go immediately to profiling, which is something we saw in the very beginning of the previous section. And then we go to fixing issues, like if I look at the profiling and then fixing issues like memory allocations, remember things you could do: reuse memory, pre-allocate memory, use views, iterators, etc. And then benchmark again and go on. If the code is not type stable, remember some ideas to look for in terms of type stuff. Promote, annotate, type, check on branches. A lot of times, like, things happen in branches where like one branch end up going in one direction, where like the type end up being something like when we saw with the 0 or val function. Check on type inference, how the type is being inferred from the previous line or the previous function that was defined or something like that. So yeah, this is usually my pipeline. I already just uploaded, someone asked if I could upload the presentation slides. I just uploaded them to the same GitHub repo. You can find them there. This is really, I just had 6 slides. And now I'm just going to go back to the next part of this.
Hey, Huda, before you jump into
yes.
the next section, someone's wondering, like right now we're developing in Jupyter notebooks. Is this how you usually develop bigger projects, or what's your setup?
Oh, yeah, no, I don't develop in Jupyter notebooks. I only use them in tutorials just because they're easy to demo. I usually use, actually, I'm just switching to VS Code right now, actually. I've heard a lot of good things about it. So VS Code seems to have a good combination of editor and terminal. So yeah, I like to have editor and terminal. All right. So moving on, the next notebook you might want to pull out is calling Python. Let's see, it's here. Yeah, so again, one thing to remember is I'm hoping that with this workshop, I will give you the infrastructure that you need to be able to switch from a platform that you're already using, for instance, like Python or C or something else, or not something else, actually. Something else happened in other workshops. I'll give references to them later. But yeah, the goal is to give you the infrastructure to be able to move. So if you already have Python code that you've already developed for another project, or you already have a really favorite Python package that still doesn't exist in, like, its counterpart doesn't exist in Julia, and you really like it and you really want to use it. Julia actually provides a really easy way to be able to interface with Python, and that's via the PyCall Julia package. So with that package, you are able to use any Python code that you've already written, or Python packages that you like to use. So this might be, let's see how this will go. This will probably be interesting, because like we'll probably run into errors. But let's just start with the most basic scenarios. So here I'm using PyCall. I'm just gonna load, get the package. And once I've used it, actually, let me restart the kernel. Okay. So here in this very first line, the syntax, what it's doing is really running 1 + 1, but it's not running it in Julia. It's running it from Python. So I call the py 3 quotation marks 1 + 1, and it's really a Python thing running in the background. All what Julia is doing is calling it. We can write complicated things. For instance, you can define your own function here. So here I'm doing py, again, same syntax, 3 quotation marks, f is function, py of sum 2 of a, and I'm adding values and accumulating things. And then the way I'm going to import it to Julia is by calling this syntax, py quotation marks, and then the function name. So once I have this function name, this sum py variable in Julia is now actually of type py object. And yeah, so if I hit the type of sum py, it's of type py object. And if I actually call sum py on a vector v, what's happening in the background is, again, the Python code is being run and not the Julia code. All what Julia is doing is calling the Python code. Okay, so this is so far from doing things in really a quick and maybe probably sloppy way on whether we're doing it on a notebook or we're doing it on a REPL. So this is how we do it here. But in most scenarios, you most likely already have a file that has your code in it. So actually you look at, I think in the repo, you will see that we have Python sum.py. So it's really, again, like a toy example where we have the same exact function that we just saw a second ago, but now it's a different, it's put in a file, .py file. So something usually happens here, and you can fix this system-wide, but this is a really quick and easy way to fix it. So I am in the local directory. So one thing you can do here is to see ls. You can see what I have in my local directory. And in my local directory, I do have that file over here, but I wasn't able to find it. So one quick and easy way to fix this is just allow basically to tell PyImport to search in the local directory. So I'm just going to do this again. And now it was able to find it. The way I will call it is via the following syntax. So once I've imported the file, so all I did here is this is the Python sum, this is the file name. So I've imported the PyImport of the file name without the .py. Once I've imported it, now I have again a PyObject file here. What the PyObject does is it's calling the PyObject dot. Now the function is kind of like an instance or a field of the PyObject that we have. So if we had multiple functions in that file, you would have had Python sum dot blah or the other function name here. So you can call more than one function name. So again, if we call the same thing here, it's also again it's running the sum function, but it's running it again in Python, but this time from the file we have already written. So this is really the standard way to import your Python code from an already written .py file. So far, we haven't got into the packages situation. We'll see how things can get a little interesting here. So first of all, I'm just going to import NumPy, for instance. So if I do PyImport of this NumPy here package, now again, I have every functionality that NumPy has. I just have it in Julia now. Well, I have it in Python. Julia is able to call it. That's what's happening. So import, again, very similar syntax. Now I have a variable name that is of type PyObject. And now I can call the variable name dot the function that I care about of v. There is, so this is really how you would import any Python package just via the PyImport functionality. So there is another package, the scikit-learn package, which does come up a lot in scientific machine learning or scientific computing. And it actually has a really cool, like an interesting syntax. I use it, actually, I use that package a lot. One way to do it is usually, so what I did here, I really just picked a completely random example. I just like went to the scikit package online and just picked some example and said, like, I'm just gonna write this in Julia. How do I write it in Julia? I just like went and took their exact same example. I think somewhere. Yeah, I think, yeah, this is it. So I just went and took their example and said, I want to write or be able to call that in Julia. So this is really, I just copied pasted it from there. The syntax is pretty straightforward. You do using scikit-learn, and then you use the macro skimport, and then here, for instance, as you can see, there's the sklearn.metrics.cluster. You don't really need sklearn because it is the scikit package, and we know it is the scikit package, and we're using the skimport macro. So all you need is really just the metrics.cluster, so skimport of metrics.cluster. And then what you're importing is this functionality, say, contingency matrix. And then you just get it that way. This is really like the main difference is just really this line to this line. And then everything else is just the same. It looks like Julia code. I mean, it is Julia code here. We're defining X, we're defining Y, and then we're calling this new functionality, which we just imported it. So we can just use the function name as it is, and everything's going to run fine. So yeah, so the same value we get. So this package can be very handy sometimes. Okay, so moving on, so far we've kind of been in a very simple scenario where we had either files that we imported or packages that are kind of pretty well known, like NumPy, and we use the scikit package from Julia and sklearn. So far it's been like nothing's so fancy. But what happens is that sometimes in your own Python version or in your own Python code, you actually have a lot of packages, and sometimes the packages your code from Julia is not going to run because the packages are not present. Now, there are two things to know here. As a rule of thumb, I think the first thing I would do if I'm running my own Python code and I want to call it from Julia is, first of all, I would make sure that the Python code actually works from whatever environment I have. One thing to notice is, yeah, I think if I do here, yeah, let me try one thing. Py import of, I think I don't have this here. Have it. Okay, great. So this is a package that I don't have. And let's assume that my code uses CVXPy. Well, I won't be able to access the functionality of CVXPy because I don't have it in the Python version that Julia is using. Now, one thing to notice here is that once I've imported it, Julia complained. It said, PyCall is currently configured to use the Python version at this location. And this location seems to not have CVXPy. I can do one of two things. First of all, either go to that Python location on my computer, because this is my own installed version of Python. This is not the Julia installed version. I can either go to that Julia, my own installed version, and make sure that my code runs from that installed version with all the imported packages found there. Or I can just use Julia's installed version or Julia's specific Python configuration to install this package. So I'll actually show you, I think if I go to, let me go to the terminal. If I do, let's say, yeah, I think I had, this is different. So let's say I'm using PyCall. And let's say I have, do py import of my graph. Okay, here's what I will do actually. I will change where Python is installed. So I'm actually going to set it to the Julia installation. Actually, let me do one more thing. Py import of CVXPy. So it's going to complain, and it's going to say, well, CVXPy is not there. What do I do? Again, I can either go to my own version of Python, or I can just use Julia's installation of Python, or Julia specific or Python specific installation of Julia. Julia specific Python distribution via conda.jl. So what I'm going to show you here is how to use the Julia specific Python distribution. I have originally changed my Python distribution where I'm using Python from. So I'm going to go back to the Julia specific version, and it's pretty easy how you can do that. The reason it's good to stick with the Julia version is because it's really easy to just install the packages from Julia once you have the Julia specific version scenario. If you're using your own Python your own Python installation, you're kind of on your own. Like, you just want to go make sure everything in your Python environment is running fine, and now come back to Julia and say, this is the Python environment that I want to use. But from Julia, you can actually just add the packages here. So what I'm going to do here is just reset this environment variable. And when I reset this environment variable, I am back to the Julia version installation. I think if I do py import of iGraph here, this is not going to work. I have it too. Okay, CVXPy. Okay. Oh yeah, I have to exit. Sorry. So yeah, this is what happened. So I messed up. Let me redo this. Let me do using PyCall. And then env Python is equal to, so I'm going back to the Julia specific version. And now what I will do is hit the square bracket, this key here, to go back to the package, or I could do using package and then do package.build. So I want to change where I'm which Python I'm using from PyCall. So package.build, or I can just do build PyCall. I see a question here. Yes, but is this something that, is this a previous conversation, setting up the distributed?
Yes, I will answer that.
Okay, cool, thanks. Okay, so I just rebuilt by PyCall. So great, and now I'm actually going to exit. Okay, I'm going back to Julia again. I'm going to do using PyCall. And I was basically changing where I'm going to use Python from. So if I do PyImport, okay, this is what I knew I wouldn't have. So a few things happened differently here. So if you remember earlier, when I was using PyImport at iGraph, everything worked fine because I was using my own Python installation. But here, I'm using the Julia specific installation. And the advantage, again, of using the Julia specific installation is that I can very easily add these packages in from within Julia. So I think if I go back to here, yeah, okay. So yeah, so I can very easily import this or install this iGraph package from Python. And I'll show you really how, like, it's very, like, it's really straightforward how to do it. So if I do iGraph Python, okay, so the format is, let's look at the syntax of PyImport conda. So you can import, as long as it's like, you can import it with conda, like you can import it through Julia. So you can use the syntax. I think if you do iGraph, and then what is the Python package? It's Python iGraph. And then the channel. Sure what I did here. Oh, no. Oh.
Huda, I think you need to put everything inside a string.
Oh my God, yes. Okay. Okay, yeah, okay. It still didn't work. Yeah, I knew this parts of the workshop's gonna be fun. Let's see, I'm pretty sure. Oh, okay. Okay. I just messed up the order. I'm so sorry. I think I just should have had this line written already somewhere. Okay. Okay. Okay, this is still not working. I'm not sure why this is going on.
I think that just really goes to show that the Python environments are hard to deal with.
That's true. I thought I had this set up and ready to go, and I didn't. Let's see how. Yeah, I think the best thing to do here is to move on with the next notebook to go back to the C situation. And maybe I can just append, like once the video is posted on YouTube, maybe we can append just kind of a 1, 2, 3 recipe list of how to actually do it. Usually it works. And of course, it's an online workshop. On the spot, it's not going to work. So anyway, yeah, I'll just upload something to the YouTube link later. Okay, so moving on to the C, calling C functions. There's the C call package that is a very handy function to use. And usually you can just call, like, the format is, or the syntax is, you have the library, you have the function, you have the input type, sorry, the output type, and then you have the inputs, and then you can just call it. You can call any, like, if you have, this is the function, this is the library, the float is the type of the input. No, the float is the type of the output. And then these are the input types. Usually there are tuples. So float 64 is going to be one of the input types. And then the input itself is 10.1. So this is usually this format. So function name, comma library in terms of a tuple. And then you have the return type. And then you have the arguments types, as we saw here. So these are the argument types. And then the arguments themselves, and however many arguments you have. So that's the syntax. A lot of times you have your already existing C code that you want to run. So here I have some C code, toy example, hello world, where this is the C code. So what you really, the only distinction that you need to do here is instead of just compiling the code and running it, you want to compile the code. So this is how I'm compiling this code. And then I'm creating this dynamic library or shared object type, or shared object file or dynamic library, depending on if you're on a Mac or Windows or Linux or Windows. And then I'm basically creating this dynamic library here for my scenario where I'm on a Mac to be able to use that library in the future. So GCC, this is the syntax here, dynamic library. Like, it depends on how you're going to create your own dynamic library. And then once you've created the library, like really any function in that library is just like, you can easily call it. So here I have the hello world and then hello world repeated, whatever the function is, then you can just read it as a function name. This is the library again, and then this is the N64. I think you don't actually need this. Yeah, so I'm just calling the library name, which I already created here, and then hello world is the function. That's the output 0, and then input, there's no input argument types or any arguments. In this scenario here, I'm doing the same thing, except that the function is different. I'm having an input, sorry, the output is also still an int, just because it's just the function return type is an integer. And the input types are int. There's only one type, so the format is still a tuple, so you want to pass it as a tuple. So that's N64, comma nothing, close parentheses. And then the input value itself is 10. So if you had more than one input value, you would have 10, comma whatever, all the rest of the input values. And then this should run just fine as well. Usually, if you want to create, like, use a C code that's going to go along with your Julia code, and like other people want to use it, it's usually good to just create a make file. I think creating a make file is probably beyond the scope of this workshop, but I'll just show like just a basic make file where all I'm doing really is just deciding on the only, like, I'm really just still running these same 2 lines that I ran just a second ago, except that I'm checking what is the operating system I'm using beforehand, so that I can either create a shared object or dynamic library. So really, there's nothing super fancy about this. Really, it's just these 2 lines and just setting up some flags and deciding on what the operating system is. So I can redo the same thing and then just make. Remember that in Julia, if you hit the semicolon key, it's as if you're back to the shell command, so like you're back to the terminal. So anything here, semicolon, ls, it's just going to work. So this is why when I do semicolon make, it's just going to work as well, because it's running it from, as if it's running it from the terminal. And then the same thing can happen here again. I'm just going to rerun this code here. And then finally, one thing you could do is use the function wrapper. So like if you have Julia hello wrapper, you can create this function Julia hello wrapper, which is going to call the C call inside. So it's going to call the C function from the inside. And that's just like a handy thing to do usually if you want to run this function a lot of times, multiple times. You don't want to write C call every single time. You can just create this wrapper on top of it. And n here is of type integer, and really all what you're passing is the C call, same strategy. What's the output? What are the input types? And what the input itself is. And this time it's an argument of your function. And then you can just, now it's like as if it's a Julia function, except that it's running something in the background. It's very similar to what we did here in Python when we did let me see. Yeah, when we imported this function, you can end up calling it Python wrapper of b is equal to this, and then it's just a function. So Python wrapper node B. So yeah, you can easily just wrap everything, just create them as Julia functions, and now all what you're calling is just a Julia function. And I think that's about it. Well, I'm kind of surprised. I thought this other section is gonna go longer. I wish we spent more time in the previous section because I skipped a couple of things. I think that's fine. I don't know if, let me see. Yeah, so yeah, we already went through this. Yeah, I guess for now, yeah, just like finally some resources are here for you if you want to work with calling rcall or R code. There's the rcall.jl package. It's pretty useful. There's the cxxwrap.jl package. There was actually a tutorial about that just like 2 or 3 days ago, a workshop in JuliaCon. So it's online now. If you haven't watched it, you can still watch it. It's on YouTube. And I mean, in general, with CXX or wrapping C++ code, the fact that we have the C call functionality is actually pretty like super useful. Like actually in the past, what I used to do is like just create C linkage to my C++ code by using extern C, and it just worked fine in the past. So really wrapping C or C++ code should be pretty straightforward in Julia. I actually have an easier time wrapping C code or C++ code than Python code. Yeah, I mean, I don't, yeah. But yeah, the point being, wrapping up, I think the section, Python, you can use it. You can use the pycall package. Usually I just use a lot of scikit-learn, so that package has been super useful for me personally. If you have packages that need to be installed, one way to do it is to install it via Julia. You saw we ran into an issue, but hopefully we'll try and fix it after this. And with C, really, it's just a C call function, and it's really just about making sure that you can create this dynamic library object, or yeah, so, or dynamic library or shared object. So it's just compiling as you used to compile and creating that object. And with that, I don't know, let me see if people have questions. Oh yeah, binary builder. Yes, can you update the Python notebook on GitHub? Yes, I will. I'll just post all of these with a postfix saying these were after, these are what were created throughout the workshop. Okay, questions? No, so performance MC or Python, in my own experience, if you're just really, let's say you have a C code and you have a wrapper of the C code in Julia, and you time benchmark the same codes on the same input, it's going to be the same. Same thing with Python. So when you're wrapping it, like really all what Julia is doing is just creating like a way to be able to call them, but everything else should be the same. How impossible is it to call Julia efficient code from Java? I don't know. Valentin, do you have any experience with that?
I know that there is Java call to call Java code from Julia. I haven't seen anything that goes the other way, but that just might be because I haven't had to deal with Java in a long while. Yeah, same here. But that's a good question. I'll look into it. It's actually also worth to mention that calling Julia from Python is pretty straightforward as well. Java, Julia. I mean, theoretically, I don't see why not, but I have never done it or thought about it, so I can't claim that it should work. To answer Andrew's question, yeah, go ahead. It's just easier to explain than to type.
That's true. I was gonna just say, like, everyone on the panel list, feel free to speak.
So in general, if you stick to the Julia default types like int and float64, you don't need to do anything special. But if you have like complicated C types, you might need to find equivalent structs. But generally, the memory layers of the different structs in Julia and in C are compatible, so you can just pass them around. If you have mutable structs, so if you have memory references, you need to be careful. But otherwise, most of the time, you don't need to write any extra C code.
I think there is something in the documentation that I'm trying to find right now that basically has like a table of like, if this is so-and-so in C, what is this in Julia? Yeah. But I don't know where it is.
It's calling C and Fortran code.
Okay, yeah.
It's the documentation I go the most often to.
Yeah, I think it's here. Oh yeah, that's great. Okay, yeah, I'll paste this link on the chat. Yeah, so there's a table in this link that I just posted to give you a good idea of how mappings work out. Could you also upload the Q&A? Is that technically, like, do we get these saved anywhere? Does anyone know?
I don't know. Maybe ping Ranjan.
Yeah. If we can, we will. Let's put it this way.
Roger, I don't know anything about FMI, FMU. So, yeah. But yeah, calling C or C++ has very low overhead. So it's normally you don't get any performance penalties. You can be fast if you write your code in pure Julia because you can do inlining across functions. But yeah, generally speaking, just calling C++ is very efficient.
Yeah, I agree.
Valerio, I think most people deploy their code in depending on what situation they run in, but I mean Docker is common. But then I work on supercomputers where Docker doesn't exist. So that really depends on where you need to deploy to, but like any other programming language.
Fair points. Yeah, for me, like I just it's mostly research code.
Yes,
boring.
You run your code on your laptop.
I mean, it's on the server still, but like still, it's not like it doesn't need to be deployed per se. Yeah, I think it depends. Yeah, depends is always a good answer. But Valentin, do you know anything about where, like in general, people like other than us, maybe, is it Docker usually?
I think that is the most common. Like, how do I get? I mean, package compiler is another option if you just want to make sure that you have a binary and you want to give that to somebody else. Best thing to do is to go onto the Julia Lang Slack and like ask there. There are many people who have different use cases and they will point you in the right direction.
Sounds good. Okay, so I think with that,
yeah, Chris confirms my statement.
Normal. Fair enough. Yeah. All right. Yeah, I mean, if there are no other questions, I think I might just like hang around for another 5 or so minutes, but that's it for me. Thank you everyone for coming. Thank you for being very, I did see the chat and the questions notifications pop up, but I didn't see them exactly. I'm really curious to go and find what Valentin and Mary and other people were doing. Thank you, Valentin and Mary, and all the panelists who were helping answer the questions. Yeah, thanks everyone for coming. Thank you, Chris. Thank you, Jeff K. Thank you, Jan. Thank you, Paulina, Alan, all of you. Thanks. Thanks, Kaj. Thanks, Ray. Shohre, Valerio. Sorry if I'm saying some of the names wrong, but hopefully they're close enough. Thank you, everyone. Yeah. Thank you, guys. Thank you. Thank you. Sorry if I was so bad. Yeah.
And I should mention, like, one of the aspects that I think is missing the most from an online-only conference is like hanging out with people and asking questions in a more like liberal fashion. So we are live on GatherTown, and they can just find other people who are also part of the conference and walk up to them and talk to them, which is rather an amusing concept for an online conference.
I agree. I think I'll try and go hang out there as well. Maybe it's later today.
Yeah, it was great fun yesterday evening.
Or if you want to come to the podcast, just let us know. Say hi. Segment. Yeah, thanks everyone for the preference repair. Make a good short book and writing good Julia code. Cool. Thanks, Arnie. Thanks, Richard. Yeah, someone asked about a Slack channel, though I completely forgot about that. What do you think, Valentine? Is it worth it to create a Slack channel? I
think Slack is, the entirety of it is very well suited, right? There's the performance help desk, there's
that's what I'm saying, yeah. So I mean, they already, like, these kind of channels already exist. Like there's, maybe I should add some resources to my slide and say where to go on Slack.
Shore, running Julia within C is possible, and there is documentation about that, but it's a little bit too involved to do as a quick tutorial.
Okay, so on the JuliaLang page, is there like a page that says resources or anything like that?
There's community, yes.
Okay.
And that points towards Discourse, and that points towards Slack and Sulip.
Okay, so Ranjan is probably gonna kill the workshop. If anyone has anything to say, let us know, or feel free to reach out to me wherever. Like, I'm on Slack, I'm on Twitter a lot, and email. My emails are online, so you can find me, or GitHub issues, I guess. Yeah, so I think Ranjan will stop the streaming in just a few minutes. Oh,